the all the theorems and corollaries in the book, at least as far as we can get. Not really proving them, but thinking about them in the context of examples. So the first main theorem in chapter 4 is called the criterion for a to the I to equal a to the j. Let's think about this in the context where we've got a cyclic group generated by an element that's got order 8. So as a set, you get this. And we've already seen that in doing calculations to figure out the cyclic subgroups generated by other elements, we've had to mod the powers by the order of the element. For example, in this one, cyclic subgroup generated by, say, a to the 6th. A to the 6th to the first power. A to the 6th squared is a to the 12th, but that's the same as what? A to the 4th, we got to mod the power by 8.
But the first one should not include a to the 8.
Yes, thank you. Technically, it's actually not wrong to write that, but it does equal e. A to the 6th cubed is a to the 18th, which, by the way, is also a to the 10th because it's a to the 6th squared, which is this, times a to the 6th. That's also the same as a to the 10th, which, again, continuing to mod by 8 is a squared. A to the 6th to the 4th is going to be a to the 24th, which is the same as either of these three things, any of these three things times a to the 6th, this, including these two, giving also a to the, oops, mistake here, what? That's my mistake. Mod by 8, okay, yeah. A to the 16th, which is the same as a to the 8th, which is the same as e. What do you notice about the relationships between the powers here? What would be a fact you could write down in relating things where the elements are equal but you have different powers? Or maybe you remember from the reading. In relationship to 8. You could say they're congruent mod 8. That's also the same as saying 8 divides what? Focus on those powers. What would 8 divide? In relation to these things.
Their difference?
Their differences, yeah. A to the I equals a to the j if and only if n divides I minus j. I'm assuming A has finite order n. Suppose A has finite order n, then a to the I equals a to the j if and only if n divides I minus j. Or if and only if n divides j minus I as well. So in this example, 8 divides 18 minus 10. It also divides 10 minus 18. Divides plus or minus 8. It divides 18 minus 2, 16. 24 minus 8 is 16. 8 divides that. 8 minus 24 is negative 16. 8 divides that. These are going to be the same also as 8 of the 32nd, 8 of the 40th, 8 of the 48th. Those are all the same. It's also the same as 8 of the negative 8 and 8 of the negative 16. Negative powers count as well. If the order of the element is infinite, when does a to the I equal a to the j in that case? Only if I equals j. Yeah. So that's more restrictive. There are corollaries. There's a corollary about the relationship between the order of an element and the order of the cyclic subgroup generated by the element, which is a long-winded way of saying, well, if you make it more precise, something fairly simple. The order of A and the order of the cyclic subgroup generated by A are related to each other. What's the relationship? You know what? I didn't want to erase that group up there. What's that relationship? That has order 8 as an element. Its cyclic subgroup, its cyclic group generated by it has order what? 8 as well. They're the same. The order of an element is the same as the order of the cyclic subgroup it generates. The smallest positive integer power of A, giving you the identity, if there is such a power, is the same as the number of elements in the cyclic subgroup it generates. What can you say about the order of an element A when you assume a to the k equals e's? So I could write something like this. Suppose we're talking about elements of finite order here. The order of a to the a is n. And suppose a to the k equals e. What can you say? Finish this for me. Example, n is 8. When else would you get a power of a giving you the identity besides the power of 8?
If k is a multiple of n, so n divides k?
Yep, then n divides k. A to the 16th, a to the 24th, a to the 32nd, a to the 40th, a to the negative 8, a to the negative 16, a to the negative 24, they all equal e. 8 divides all those numbers. And you can consider more examples if you don't want to focus on the proofs right now. Focus on examples to see this, to make empirical observations. There's a corollary about the relationship between the order of the product of two commuting group elements and the order of the elements themselves. The order of the product of two commuting elements is related to the order of A itself and the order of B itself when AB equals BA. Cyclic groups are abelian, remember? So this kind of relationship is going to hold with cyclic groups. Or whatever kind of relationship we're going to say there is going to hold. I haven't written it down. Without listing out the cyclic subgroups generated by different elements, just let's think in our minds here. The order of A squared is going to be 4, right? The cyclic subgroup it generates is going to be E, A squared, A to the 4th, and A to the 6th. 4 elements. And the order of A cubed is going to be, oops, let's do A to the 4th. I'm going to do A to the 4th. Order of A to the 4th is going to be 2. Right? A to the 4th squared is E. What's the order of their product? the order of 8 to the 6th. What's the cyclic subgroup generated by 8 to the 6th? A mod by 8. It's got order 4. So is there a relationship there? Well, it's not that this plus this equals that, or this times this equals that. And you'd want to do more examples before you were more certain of what I'm about to say. But it is true that the order of the product 4 does divide the order of 4 times 2. It divides 8. And that is the true thing you can say in general. In this context, the order of AB divides the order of A times the order of B. In the example over there, 4 divides 4 times 2. 4 divides 8. Again, you wanted to be more sure, you should probably consider other examples. We're not going to take the time. This one is, I think, perhaps the trickiest one to formulate. There's a theorem about the orders of powers of elements of a finite order and generators of the cyclic subgroups generated by those powers. That's kind of confusing sounding. Well, again, let's keep this up here. Actually, I'm going to rewrite what I just erased, pretty much. The order of A squared is 4. Note that 4 is also 8 divided by 2. And 8 is the order of A, and 2 is the power there. I wonder if that is going to be a true thing in general. Well, if you think about it, it's pretty clear that it's not going to be a true thing in general. But maybe we can modify it. The order of A to the 6th is also 4. This generates the same cyclic subgroup as A squared. And 4 is, again, 8 divided by 2. 2 is no longer the power there. Maybe we need more data. Are they still related in some way? The order of A to the 10th is the same as the order of A squared because A to the 10th equals A squared is also 4, which is also still 8 divided by 2. So again, you can't take that number and divide by these powers, but is there a relationship that all 3 of these numbers, 2, 6, and 10, and I guess the next one would be 14. Do those numbers in relationship to 8 share a property? You could say the difference between each successive power is 8 divided by 2. Is that the main thing you want to focus on? Not necessarily. If you think about it more and if you experiment more, you can notice that comparing 2 and 8, comparing 6 and 8, comparing 10 and 8, 14 and 8, and thinking about the GCD of those numbers, of those pairs. GCD of 8 and 2 is 2. The GCD of 8 and 6 is also 2. The GCD of 8 and 10 is also 2. The GCD of 8 and 14 is also 2. And 2 is the thing we keep dividing by in all these things. Maybe that's the thing you divide by in general. Let's test it out with another example. Even within the same example, what's the order of A to the 4th? It's 2. 2 is 8 divided by 4, which which does happen to be the power there, but 4 is also the GCD of 8 and 4. And 8 to the 4th would be the same as 8 to the 12th. And the order of that element would be 2, which is also 8 divided by 4. Is 4 the GCD of 8 and 12? Yes, it is. Is 4 the GCD of 8 and 20? Think about it. Yes, it is. Again, you can gather more evidence to try to confirm something like this. Let's just jump to the punchline. Suppose the order of an element is n. Then the order of a power of that element, if this pattern holds true when you check it with other examples, should then be n divided by the GCD of k and n. And that is true. And if the GCD of k and n happens to be 1, special case. Listen carefully. If the GCD of k and n happens to be 1, if k and n are relatively prime, if k and n are relatively prime, so GCD of k and n is 1, then the order of a to the k is n divided by 1 is n. And therefore, a to the k must be a generator of the cyclic subgroup generated by a. And thus, the cyclic subgroup generated by a is also generated by a to the k. Coming back to our example, the generators of this group here, this cyclic group, are going to be a itself, also a cubed, also a to the 5th, also a to the 7th. 1, 3, 5, and 7 are the positive integers less than 8 that are relatively prime to 8. And it'll also be generated by a to the 9th, and a to the 11th, and a to the 13th. As well, you can do higher powers, but of course those powers, like a to the 13th, are the same as lower powers. A to the 13th would be the same as a to the 5th. Focusing on the lower powers, a to the 1st, a to the 3rd, a to the 5th, a to the 7th, 1, 3, 5, and 7, those are the elements of U8. Is that always hold? Yeah, because UN consists of positive integers less than n that are relatively prime to n. So when considering cyclic subgroups generated by elements of order n, whether you do it in the abstract or whether you think about Zn under addition, the generators, when you take them to be less than n, simplest form, are the same as the elements of Un. 1, 3, 5, and 7 in this example. There are corollaries to this. The order of an element in a finite cyclic group in relation to the order of the group, it divides the order of the group. The orders of elements over there in that example are 1, 2, 4, and 8. 4 possible orders for elements. They all divide 8. They all generate cyclic subgroups of those orders, 1, 2, 4, and 8. And those are actually the only cyclic subgroups of those different orders, of those different divisors of 8. Criterion for powers of a generator generating the same subgroup and having the same order. Turns out if your order of A is n, the cyclic subgroup generated by A to the I will equal the cyclic subgroup generated by A to the j if and only if the GCD of n and I is the same as the GCD of n and j, as we were seeing back over here. Those GCDs were all the same. Generators of finite cyclic groups, again, would be, for the given A to those powers that are relative prime to n. And those would be the same as those powers would be the same as the elements in un when you take them to be less than n and positive still. And there's a certain number of them that we're going to talk about in a minute. In the context of Zn, again, just remember the group is addition mod n. So Z8, for example, generators of Z8 are 1, 3, 5, and 7. But remember, the operation is addition, not multiplication. There's something called the fundamental theorem of cyclic groups. That essentially says pretty much everything you'd want to know about cyclic groups. Cyclic groups are the easiest kinds of groups to understand. What are the types of subgroups? The subgroup of any subgroup of a cyclic group is also cyclic. That's what I mean by type. And therefore also abelian. Cyclic groups are abelian. The order of any subgroup of a cyclic group must divide the order of the group. That's actually a fact that generalizes to arbitrary groups. We will see in chapter 7. The order of any subgroup of an arbitrary group divides the order of the whole group. It's easier to prove with cyclic groups, but it's also true in general. How many subgroups do cyclic groups have? Cyclic groups have exactly one subgroup. It's unique for every divisor of n. So if you've got a cyclic subgroup of order, say, 60, got a cyclic group of order 60, whether you think about it like this or like this, it's got exactly one subgroup of every order that divides 60. The divisors of 60 would be 1, 2, 3, 4, 5, 6. Hopefully I don't miss any. 10. Now I can just go 6 times 10 is 60, 5 times 12 is 60, 4 times 15, 20, and 30, and 60. The divisors of 60, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Therefore, there are exactly 12 cyclic subgroups of a cyclic group of order 60, one for each of these orders. And these are the orders of those subgroups. You can make what are called subgroup lattices. I will skip that for today. We'll come back to that next Monday. With the time we have remaining, I want to briefly talk about the Euler phi function. that you should have read about. Euler phi function, or phi function if you prefer. I will always say phi. This function takes a positive integer as input, bigger than 1, and tells you the number of positive integers less than the input that are relatively prime to the input. Make a table here. How many positive integers less than 1, less than 2 are relatively prime to 2? Just one of them. 1. And it happens to be 1. That's also the one that's relatively prime. How many positive integers less than 3 are relatively prime to 3? 2 of them. 1 and 2. How many positive integers less than 4 are relatively prime to 4? That's 2. 1 and 3 are the positive integers less than 4 that are relatively prime to 4. Phi of a prime is always 1 less than the prime. Phi of 5 is 4. 1, 2, 3, 4 are all relatively prime to 5 because 5 is a prime. 6 has 2 elements, 2 positive integers less than 6 that are relatively prime to 6. 1 and 5, right? 2, 3, and 4 all are not relatively prime to 6. 7, phi of 7 is 6, 8, phi of 8 is 4, right? 1, 3, 5, and 7 are the positive integers less than 8 that are relatively prime to 8. There's 4 of them, etc. By what we've just said with these examples, it should be clear, thinking about, for example, these examples, that the number of generators of a cyclic subgroup of order n is phi of n. The number of generators of a cyclic group of order 5 is 4. The number of generators of a cyclic group of order 6 is 2. The number of generators of a cyclic group of order 8 is 4. That's a fact. Mathematica's got Euler phi built in. And you just type it as Euler phi with a capital E and a capital P. Euler phi of 8, for example, is 4. Euler phi is kind of behaves in an up and down way. Sometimes it gives you a big value. I mean, generally speaking, as the input gets higher, the output also gets higher. Oops, Euler phi. But there are ups and downs. There it's going higher, back down lower, back up higher. It's going to be pretty high for primes, right, relatively speaking. You can plot it if you like. There it is. Generally speaking, the trend is upward, but lots of ups and downs. The relative maxima, if you will, occur at primes. 17, 19, 23, 29, 31. Is there a formula for Euler phi? Well, there's a partial formula in what you might call an algorithm. Actually, you could convert it into a regular formula too, but it's more complicated. The book does describe it. You can think about that and test it. All right, we'll see you on Monday.